Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit where we're continuing our AMC 10 and 12 problem reviews. We are now 3 weeks away from the AMC 10 and 12A exam dates, so there's still time to prepare, and I'd recommend you check out our blog, as I've mentioned before, if you want some tips for how you can prepare in these last couple of weeks. Now, our first question we will work on today is number 25 from the 2004 AMC 10B. Now we have a diagram here. We have a small circle of radius 1. It's tangent to two circles of radius 2 at these points we can see in the diagram, and we have this AB as the diameter in that case there. Now we want this shaded region, so it's inside the intersection of the two bigger circles, outside that little inner circle there, and we're going to find that, and it shouldn't surprise you that we're probably going to find that overlap region first. Right, so we want to focus on this full overlap region, this kind of I shape there, including the center, right? So we want to find that whole region, including the center, and then we can X out that region in the middle that we don't want there. Now, if we're kind of starting to recreate this picture, let's draw it a little bit bigger in a diagram we can work with. One of our key ideas is that we have AB. Let's start with AB. That is our diameter. So we have our point A, we have our point B. That is a diameter. And note it's also the radius of the two outer circles, because those circles each have a radius of 2, right? The inner circle has a radius of 1, so its diameter is 2 there. So this 2 is a radius of that outside circle, both of them as well. Now, the key thing here is, and this is a pretty common trick for circle problems, right? Circles, pretty much all we know about circles is that it's a collection of points that are some radius, right, away from the center. So if we have one radius, why not draw some more? So notice that AC, so if I connect A to C, that is another radius of the big circle. And likewise, BC is another radius there. So our kind of key observation here, I'm not going to label all of these 2's or anything, but the key observation is that all of these are radii. We have a bunch of radii here. So both of these triangles are equilateral. So triangle ABC. This is, of course, congruent to triangle ABD. And they are equilateral triangles in this case. So these are equilateral triangles in this scenario. So we have all of these equal lengths. Let me not worry about the 2 for a moment, but we have all of these equal lengths there. And we know then that we have a bunch of 60-degree angles there. And so in particular, what's going to be important about these angles is that we actually have 120-degree angles for CAD and DBC as well. So those are 120-degree angles in that case there. So now we can start constructing our shaded region here. So we're going to have some areas of sectors and equilateral triangles, things like that as well. So how is this all going to work? Well, let's do it piece by piece there. So first of all, right, I haven't drawn our circle shaded region, but if we look at our CAD, we look at this here, and then I'm going to draw this a little bit exaggerated, But then if we have our circular region over there, that is a sector. So that area there is a 120-degree sector. So we have what fraction of a full circle? 120 divided by 360 times the area of a circle, pi 2 squared. So that is our sector there that we have. Now, we need to add to that the bottom piece. Notice that if we have some overlap here, right? So we have some overlap then in that case. We do have another sector. So we actually have an identical sector there. I'm still going to write it out just so we have all of the work in that case. So we have 120 divided by 360. So we have a third of a circle again there. And that gives us our bottom sector, and we have our whole shaded region in that case. However, we still are overcounting these two equilateral triangles in the middle. That's not so bad though, because we know how to calculate the area of an equilateral triangle, hopefully. There's two of these. They each have a side length of 2. The area is s squared, side length squared, square root of 3 over 4. Now, don't forget, we needed to subtract that circle as well. So we had that circle of a radius of 1. So we have minus pi times 1 squared in that case as well. Right? This is our whole area of the region we're looking for here. So that is our shape. I'm leaving myself a little spot on the bottom to simplify this. So in terms of pi, we have 1/3 times 4 pi, another 1/3 times 4 pi. All right, so that is 8/3 pi minus a full pi. So we have 5/3 pi here. That already narrows down the answer choices quite a bit. And then we have, right, our equilateral triangles each have an area of root 3. So we have minus 2 root 3 there as well. So we have minus 2 root 3. And this gives us a final answer then here of B. So our final answer, we had that 2 sectors minus the 2 equilateral triangles minus the circle, 5/3 pi minus 2 root 3. Okay, let's move on then to our second question here. The second question is a little bit tricky. This one has a nice trick in it. We're looking at these 2004 powers of 2. So we have 2 to the 0, 2 to the 1, 2 squared, etc., etc. And we're looking then for, right, how many of these have a first digit of 4? If we saw last digit, that's clearly modular arithmetic, different things like that there. But let's see if we can start looking for a pattern here, things like that as well. Now, I'll erase some of this work in a moment, but if we just start writing out some powers of 2, we have 1, 2, 4, 8, then we have 16, then we have 32, 64, then we have 128. Notice here, I'm writing these out in kind of a specific way as well. We have 512, I'll stop here with 1024, things like that there. Now, right, we can organize these things in terms of the digits, right? So we have 1 digit, 1, 2, 4, 8, 2 digits, 16, 32, 64, right? And start looking for some patterns in their first digit there. So I'll organize this in a couple of different ways as well. But to start, let's think about a chart. So if we have the number 1, right? Notice that this is our first digit. If the first digit is 1, so think like 1, think like 16, 128, right? Notice that doubling that doubling that number, we're always going to either end in, right? We have to next have a first digit of 2 or 3, right? Think of this as doubling, but maybe you have some carrying in those kind of other digits. So it's possible you could get up to a 3 in that case. But nothing else, right? Nothing that starts in a 1 times 2. There's no way you can get a 4 from that kind of next term there. Right? But, right, what can happen from this case? Well, we don't necessarily see examples of all of these in what we have written, but following this similar pattern, right, the 2 goes to a 4, right? Or we could go to a 5 in that case. The 5 will have to start over. The 5 has to go back to a 1. So let me kind of highlight the 5 here as an ending point. The 4, however, either goes up to an 8 or a 9. Again, right, we don't see examples of these necessarily in our list, but it shouldn't be too hard to understand, right? Okay, we're either doubling or doubling plus 1 because of some carrying going on there too. So from the 3, we either go to a 6 or we go to a 7, and those are ending points again. So when we end doubling a 6, we'll have like a 1, 2 or a 1, 3. But I want to point out here, and it's important, that all of these ending points, so no matter which point you are at here, they all go back to a 1. So we have this kind of symmetry stuff going on where we're looping out, we have this grid growing, but then once we get to the next number of digits, we always start over at 1 in this case. So let's think about these patterns a little bit here. So, right, one pattern we definitely have. You can have for a digit of 1, then you can have a 2, then you can have a 4, then you can have an 8. Or you can have a 1, you can have a 2, you can have a 4, you can have a 9. Or, right, you have a 1, 2, 5, and then it starts over, or you have a 1, 3, 6, and then it starts over, or a 1, 3, 7, and then it starts over there. So let me shrink this down a little bit here, but these are kind of the different patterns that we have in this scenario. Now, couple of things I want to note and start thinking about here. First of all, let's look at these in 2 sets. There's a couple of observations that are key to this problem. So we have 2 possibilities for working through the digits, right? Like 1, 2, 4, 8, but this could also be like 1024, 2048, 4096, right, etc., right? You're working through the set number of digits. 2 of these possibilities have a set of 4 powers in a row. And the other 3 that we have are going to be sets of 3. So we have these 2 possibilities there as well. Now, there's a couple of key things in the problem now that I want to look back on. First of all, let's remind ourselves what the question is asking about. The question is asking about how many of these have a first digit of 4. Notice that those 4s only appear in this first set. So if we started looking at these, and let's say we had for this first set there, let's say we have X sets of these groupings, right? So these kind of X patterns will occur there. Every one of those sets has 1 4. So actually, if we can figure out how many times does this pattern appear in the first digits, that will tell us how many 4s appear there. Now, we can also look and say, let's suppose we have Y sets of these in this case. Now, here's where the magic starts to happen. Now, we have in our set S, 2 to the 0, 2 to the 1, 2 to the 2, all the way up to 2013. So in total, we should have 2004 powers of 2. Well, they come in sets of 4. How many sets of 4 do they have? We have, well, X of those. We have 3 sets, we have Y sets of 3. So, right, no matter how this happens, this is how we should get our 2004 total numbers in this problem. We have 2004 powers of 2. All of those numbers come in a set of 4, and there are X of those. Each of those have 1 4, which is what's going to be important for the answer. So we really want to know what X is here. Now, you might, when you're first reading the problem, think that they give us some extraneous information. They give us some information we don't need. But actually, this first sentence is our key to solving the problem with this trick. So the next number in our sequence, right? We went all the way up to 2 to the 2003. 2 to the 2004 has 604 digits, and its first digit is 1. So that means that that's a start of a new set, right? 2 to the 2004 is going to be at the start of a new one of these sets in this scenario. And that's actually telling us how many sets we have in total. So if 2 to the 2004 is the start of a new set, well, it's the start of the 604th set because it's a 604-digit number, right? Notice anytime we're going back to 1, that's because we're adding a new digit. So our 2004 numbers have to come in 603 sets there. And this, by magic then, well, really by solving this system, allows us to solve for X, right? So we triple this, so X is 2004 minus 3 times 603 if we're solving this system, and we get that X is 195. So just by solving this system of equations here, we don't know exactly how many sets appear kind of in the first way or the second way, etc. But we know that there are 199 sets of 4 numbers. Each one of those has a single 4 in it. So our final answer is B. We can answer this that way, just counting these patterns and how many times each pattern occurs in the problem. Okay, that will be it then for this video. Hopefully these problems, which were pretty tricky, make sense now that we talked about them. Let us know if you have any comments below. Right, give this video a like if you enjoyed it, and I hope to see everyone next Thursday for some more problems. Goodbye.